Good evening, ladies and gentlemen. This video will be about trig-inverse trig functions. So what I mean by that is, let's say you take sine of arcsine x. Now that's obviously equivalent to x. You need to take into account the range of arcsine though. So that will mean it's equivalent to x between -1 and +1. Let's say instead you take sine of arccos x. What is that? Well, that's what I'm about to show you. The scope of this will require basic trigonometry and some competence with algebra. Okay, let's get started. So then, how do you define a circle? Perhaps you might say it's something that has the same width wherever you measure it. That's not the case. A circle would fail this test, and as you can see in this diagram, you can measure it between these 2 points and get a wildly different number to these 2 points. If you measured the distance through the centre, then a circle would pass this test. If instead you define your circle as something with a constant width when measured through the centre, then that's not quite the case, because this is a rouleau triangle and this indeed passes this test. If you follow this line, you can see the distance here it's always the same. Perhaps more easily shown is the length of these lines on the outside. The length of this line here plus the length of this line here always seems to come to the same number, and it's a constant length line, so the rouleau triangle has a constant width when measured through the centre. We can draw a rouleau triangle by taking one point on the edge and drawing a circle around it. And then let's take this point and draw a circle around that, and finally this point and draw a circle around here. You can see we have 3 arcs that all join up, and just remove the rest of the circles and there's your rouleau triangle. Perhaps another definition of the circle, you might say, would be a shape with all the points on the edge being the same distance from the centre. And indeed, if you take this centre and take a certain distance around it, you just do different angles around this centre and do all these points the same distance, then you are forced to form a circle. On a slightly different note, take this grid here with these 2 points, 1, 1 and 3, 2. How would you find the distance between them? Anyone who has studied GCSE mathematics would instantly tell you Pythagoras. Well, how would you do that? You take the x increase and the y increase, and that forms your a squared and your b squared to get your c squared. Delta x is 2 and delta y is 1. We can form the hypotenuse squared by just doing delta x squared plus delta y squared, and then we can find the actual hypotenuse length by doing the square root of that. Bearing in mind that square root is a positive function, so it will always be a positive distance, and also square roots can only take positive inputs, but that's okay because squaring these two is always going to be a positive number, or 0, and zeros are fine with square roots. So from that we get 2 squared plus 1 squared, which is just 5, so our length here is indeed root 5. Now root 5 is approximately 2.2, and you can see how this is appreciably a little bit more than 2 units long. So let's try another example. So we want to find the distance between 0, 0 and 0.707. Now those among you that are more to grips with your square roots will realise that this is 1 over root 2. Again, we form our triangle and get our delta x, 1 over root 2, delta y, 1 over root 2. So hypotenuse squared is delta x squared plus delta y squared. Square root that, and 1 over root 2 squared is obviously a half, and a half plus a half is just 1. Now that seems a bit curious. How did I know that was going to be 1? That's obviously been set up, hasn't it? Not just any number gets you a length of 1. Are there any other points that will have a length 1 when measured from the centre? We have this point here, 1 over root 2, 1 over root 2. But of course, because it's a square, the hypotenuse squared is x squared plus y squared, we can make one of them negative. And indeed, negative 1 over root 2, 1 over root 2 is another point. Carry that across, 1 over root 2, negative 1 over root 2, and negative 1 over root 2, negative 1 over root 2. Are there any more points? Because there can't just be this 4, can there? that circle, that could have length 1, there must be lots. Well, if we start with the coordinate axes, we know there's 1, 0. 1 squared plus 0 squared is 1, square root 1 of 1. There we go, another length 1. And just the same, use the y-axis instead of the x-axis and make them negative. And you can see this starts to form a circle. If we had a few more points that we could fill in, then that's appreciably a circle. So on a genuine circle, take a arbitrary point, let's take this one here. Let's say x is 0.2 and the distance is 1. What's the y value? So we'll have to do a bit more algebra and rearranging. So we know r squared is x squared plus y squared, and hypotenuse is 1, so 1 equals 0.2 squared plus y squared. 1 squared is just 1, and I've made that simplification here. And then we want to find y squared, so we put 1 minus 0.2 squared on one side and y squared on the other side. Square root that, and the value of that is 0.980, and this is very close to 1. That looks like it could be true. So for a general point, let's take this one with r1, x of y are to be determined. We want to find y as some sort of expression in x. So we can form our Pythagoras equation again, and that's 1 is x squared plus y squared, and then if we put y on its own side and x on another side, square root it, y equals the square root of 1 minus x squared. Because the square root is only a positive function, that's the equation for a semicircle. Therefore, f of x equals the square root of 1 minus x squared draws a semicircle. Once again, let's take a point on our circle radius 1, and it will be 30 degrees above the x-axis. And then we want to find out x and y. And how do we do that? Well, we can form a right angle triangle and do some basic trigonometry. Using sqrt, we know that sine theta equals opposite over hypotenuse, and cos theta is adjacent over hypotenuse. Sine theta is opposite, so that's y over hypotenuse, which is 1. And cos theta, or cos 30, is x over 1, because the adjacent is x and the hypotenuse is just the radius. And turning these into actual values, we know that sine 30 is a half and cos 30 is root 3 over 2. Again, taking a general point in our circle radius 1, for any angle theta above the x-axis, what is x and what is y? So sine theta is opposite over hypotenuse, cos theta equals adjacent over hypotenuse as per normal. Sine theta is y, cos theta is x. That's just from the same thing previously, but now we're not trying to work out the angles. Again, I want a function of y in x. We know what cos theta is, and we know what x is, we know what sine theta is, and we know what y is. But what is actual theta? Well, of course, we can take the arccos or inverse cos, or cos to the minus 1 you may have seen it as, and theta equals arccos x. And then it's now quite easy to see that y equals sine theta, y equals sine of arccos x. If you look at our graph again, you know that x squared plus y squared equals 1, and that's from Pythagoras, of course. But we also know that cos theta is x and sine theta is y. So if we swap those out, we now have cos theta squared plus sine theta squared is 1 squared. Again, that's just from Pythagoras, and you may recognise an identity you are taught in GCSE mathematics. Sine squared theta plus cos squared theta equals 1. But from that we have f of x equals sine of arccos x draws a semicircle. Again, arccos x is a positive function just like the square root, and that stops it being a full circle. Functions cannot have two outputs at once. But this would imply, surely, that f of x equals sine of arccos x is the same as f of x equals square root of 1 minus x squared. And indeed that's correct. They draw the same curve, they have the same domain and range. And you can try some values for yourself and they do indeed match up.